So welcome to the 9th video in Special Relativity and the first video in Special Relativity 2. In the last series of videos on Special Relativity, we looked at how to transform between space and time coordinates. So we looked at how different positions in space-time looked for observers moving with relative velocities to those positions. In this video, we will extend that and we will look at how velocities transform. So instead of looking at objects with fixed positions, we will be looking at objects moving with some speed in one reference frame, and we'll be looking at how they appear to move when viewed from a second reference frame, moving with respect to the first. And so from that, we can then look directly at the relativistic version of Newton's second law in terms of momentum, which also then leads us on to relativistic energy. So we'll start with our familiar scene. We have a man with his reference frame, which I have called S. And so S refers to his XYZ T coordinate system. And we have our rocket ship, which is travelling with a velocity u in the x direction, so ux, relative to that man. And I'm going to call the reference frame of that rocket ship S dash. So that is the quantities, so x dash, y dash, z dash, and t dash. And these will be our standard definitions. So our rest reference frame is S, so that's the reference frame that we're observing from. And the reference frame moving with a relative velocity to that is S dash. And so now we will introduce a third object onto our scene, and that's a meteorite, and it's travelling past our man with a three-dimensional velocity v. So it has a velocity components vx, vy, and vz as viewed by the man, so in the reference frame S. And what we're interested in is how that meteorite is moving from the point of view of a person in the rocket ship. So we want to find the velocity of the meteorite in our reference frame S dash. So we want to find v dash, or the components vx dash, vy dash, and vz dash. So that is, we are looking for the Lorentz transform of our velocity of our meteorite. So we'll start by looking at vx. We know that vx, our velocity in the x direction, is equal to the rate of change of position. So that's dx dt. And we also know then that in the rocket ship's reference frame, we have our velocity vx dash, which is equal to the rate of change of position, which is dx dash dt dash. So a Lorentz transform gives us the relationship between these two terms, vx and vx dash. And so to get that, we will be looking at our two Lorentz transforms we already have for position and for time. We know that the Lorentz transform for x dash is that x dash is equal to gamma times x minus ut. And so we can show that dx dash is equal to gamma times dx minus ux dt. Once again, where ux is the velocity of the reference frame of our rocket. And likewise, we have that formula there for dt dash. And if we substitute those two equations into our original equation for vx dash, the velocity of our meteorite as viewed from our rocket, and we simplify, we get that vx dash is equal to vx minus ux divided by 1 minus ux vx on c squared. So remembering that in this equation, ux is the velocity of the rocket's reference frame. So that's the velocity of s dash as viewed from s. So that's the velocity of the rocket as viewed by the man. And vx is the velocity of our meteorite, also as viewed by the man. So now we can do the same trick for the y and z components of our meteorite velocity. So that's vy and vz. So we start once again with our formula for the velocity as the rate of change of position. We know that the rocket is not moving relative to the man in the y direction, so that dy dash is equal to dy. However, since there is a relativistic velocity, there is still a time dilation effect. So dt dash is equal to gamma times dt minus ux dx on c squared. Once again, so that's the same formula as we used to find the velocity in the x direction. And then we substitute those equations back into our original equation for v dash y and simplify, and we find the Lorentz transform for the velocity in the y direction. And we do exactly the same for our z direction with exactly the same logic. So even though we only have a relative velocity between our reference frames in one direction, in the x direction, so the rocket is only moving relative to the man in the x direction, there is still a Lorentz transform for all three velocity components of the meteorite. So this occurs since there is a time dilation effect, and our velocity is the change in position over time. So our velocity depends on the time. So now we have the Lorentz transforms for the position, the time, and the velocity for two reference frames travelling with a relative velocity in only one dimension. So travelling with velocity relative to each other in one dimension. The velocity transform is for a third object travelling with a velocity v relative to the reference frame s, so relative to our man.